This webcast looks at Worksheet 8E, Problems 9 and 10. Let's start with Problem 9. Here we have a situation where we're going to use an energy conservation diagram, and we're going to calculate the amounts of energies to come up with a specific answer. So the situation is that we have a rock that's going to be shot up vertically in the air with a slingshot. And it says the slingshot has been stretched 0.3 meters. So the slingshot here, let's see, this is like a spring. Okay, the slingshot, the stretchy part of it is able to deform and then go back to its original shape, so it can store elastic potential energy. And it says there is no air resistance. Okay, so at position A, we have the stretched slingshot, and notice right here where it has the rock, that's that little blue ball next to the 0. So the height is 0. It's considered on the ground, or at our 0 reference point there. And let's see what, oh, it's not moving, right? Not moving yet. But when we look at it at position B, the slingshot is back at equilibrium, right? It has returned to its original shape. Look here, the velocity is 0, so it's not moving, and it is much higher. Okay, so we've got kind of an understanding of the two positions. First, let's fill in the circle in the middle, what is our system here? We're going to just put everything we see. So I see the rock, the slingshot, and the earth. Sometimes a problem tells you what to include in the system, but if it doesn't, a safe way is just to include everything that you see. Okay, at position A, I'm just going to set myself up to think about what kind of energy, how is it stored initially? There are only a few types of energies that we're considering, mechanical energies. There's gravitational potential energy, kinetic energy, elastic potential energy, and dissipated energy. Let's take them one at a time. Does it have any gravitational potential energy? No. The height is 0, so Eg is 0. Does it have any kinetic energy? No, it's not moving. Does it have any elastic potential energy? Yeah, it has a lot of that because the slingshot is being deformed and it's a reversible deformation. Okay? And then let's look at it at position B, and let's see which of these energies it has stored at position B. Okay. Is there any gravitational energy? Yes, it's at a much higher position. Does it have kinetic? No, it's not moving. Does it have elastic potential energy? Nope. The slingshot is back at equilibrium. Has there been any energy moved to the dissipated category? No, because it said assume no air resistance. So all of the energy that we had at the beginning is now stored as gravitational potential energy. And so I could write the conservation equation here. The change in the elastic potential energy equals the change in the gravitational potential energy. That equation explains this situation. And now it says, what is the peak height of the rock? Okay, so I'm going to take my conservation equation and I'm going to plug in the formula to calculate each type of energy. For elastic potential energy, that formula is 1/2 the spring constant times the displacement of the end of the spring squared. The formula to calculate the gravitational potential energy is the mass times 9.8 times the height. Okay, and that's what I'm looking for, right? I'm going to solve for the height at position B. Okay, and so let's plug in what we know. They gave me a K of 100 newtons per meter, and they gave me a displacement of 0.3 meters. I have to square that displacement. As I'm plugging these in, I'm just checking, and they gave me the mass in a non-standard unit. It's 500 grams. So 500 grams, I need to convert to kilograms, and 1 kilogram is 1,000 grams. So that is 0.5 kilograms. Okay, so that's what I want to plug in, is the number in standard units. G is 9.8, H. So now all I have to do is solve for that H. And I get 0.918 meters. That's the answer that we're looking for. Okay, let's go ahead and look at the next problem, which is number 10. So here we have a roller coaster, and we want to know the final velocity of the roller coaster. Ooh, and look at this. It says assume that 10% of its energy is dissipated due to friction. Okay, so at position A, the roller coaster is at the top of the hill. It's not moving. It's very high above the ground. And at position B, it's moving fast and it's on the ground. Okay, so I'm just trying to make sure I understand my positions here. Again, I'm going to put everything here in the system because it's not telling me to leave anything out. So I've got the roller coaster, the track, and the earth. Okay, so let's go through. I'm going to set it up first for the types of energy, and then I'm going to decide what I have on each side of this. So at the beginning, at position A, it is not moving, but it is very high. There's nothing in this system that is elastic, right? I don't have a spring or anything that can be stretched and pop back to its original shape, so there is no elastic potential energy. At the beginning, all of the energy is stored as gravitational potential energy. Okay, they tell me that 10% of that original energy gets dissipated. So I know that there's some dissipated energy at position B. And then at position B, it's on the ground. So there is no more EG, right? It's moving fast. There is kinetic energy. And so look here. I'm going to put the rest of the energy as being stored as kinetic energy. Let's write the conservation equation. The change in the gravitational potential energy equals the change in the kinetic energy plus the change in the dissipated energy. Okay, now that I have my conservation equation, I want to proceed into solving this. And so I want to take and plug in the formula to calculate each type of energy. Gravitational energy is mgh. Kinetic energy is half of the mass times the velocity squared. The dissipated energy, I do have a formula for that, but here they tell me that it was 10% of its original energy. So 10% is 0.1, or 1/10, of the original energy, which was mgh, right? Okay, I've got a term that has mgh on both sides of this equation. I want to move all of the terms with MGH to one side. So over here I have 1 minus 0.1 times MGH equals 1/2 MV squared. And I like to circle or just be clear about what I'm solving for. I'm going to solve for the V at position B. That's the final velocity. Okay, and I think I know everything else. 1 minus 0.1, that's 0.9. The mass here is 40 kilograms. G is 9.8. The original height, they told me that. They said it's 5 meters high. If I plug that in, 1/2 of that mass times V squared. So now all I have to do is solve for the V. And so I get 9.391 meters per second.